Right, in this video we're going to look at the subject of trigonometry. We're going to start with the radian measure. This is versus the degree measure. So most of us will be familiar with the degree measure of the angle. So here we're going to introduce the radian measure. But before we talk about the radian measure, let's just cover some basics in terms of angles. So an angle is formed when two half lines intersect. So the way we're going to think about it here is if you imagine that we start with two half lines coincident, and then if we take one of the lines and tilt it upwards, the red one in this case, for instance, until it gets to that position. So the red one, oops, we have lost both of them. So just this one, purple one is here, and then the red one is now. Okay, so the position in which both lines started, we're going to call that one the initial position. So this is going to be the initial side of the triangle. The position in which the red one, in this case, finally lands, we are going to call the terminal side. Okay, so your angle is going to have a terminal side and an initial side. Then the point at which the two lines meet is called the vertex. Now this was tilted upwards or counterclockwise. So angles formed in this way are termed positive angles. So this relates to the fact that the tilt is going upwards. If the tilt is downwards or clockwise, then the angle formed that way is going to be designated negative. Right, okay, so that is going to be good enough as far as the basics of an angle are concerned. Now, so let's talk about the radian measure. So the first thing we're going to note is that the first four letters of this word are similar to the first four letters of the word radius. So that is going to give us a clue that radians are going to be related to or are going to be defined in terms of the radius of a circle. Okay, so suppose we have this circle here, center there. If the radius of this circle is r, okay, then if we measure along the circumference an arc which is the same length as the radius, then the angle subtended by that arc at the center is called 1 radian, okay, which we are usually going to abbreviate 1 rad. Now, in order to get a relationship between the radian and the degree measure, we're going to use direct proportion. So you can say that the radian is defined in terms of the arc length. So if the arc length is equal to r, then the angle is 1 radian. Now we're going to imagine the case where the arc length is the whole circumference. So if you go right around here, then the whole circumference is 2 pi r. Now in terms of direct proportion from here to here, we multiplied by 2 pi, so that means even on the other side must multiply by 2 pi. So that means the angle is subtended by the whole circumference in radians is 2 pi radians, but we know that that angle in degrees is 360, so that means this thing here must be equal to 360 degrees. So this must be equal to 360 degrees, and so this is the relationship between radians and degrees. If we divide both sides by 2, then we have got pi radians is equal to 180 degrees. So this is the one that we are typically going to use every time. Now notice that radians will typically be expressed in terms of that pi there, as we will show in examples below. Okay, so suppose we have these angles here that we want to express in radians. So this is how this is going to work. So we know that 180 degrees is equal to pi radians. Then 90 degrees by cross multiplication is going to be pi radians times 90 degrees divided by 180. So the thing that we're going to notice here, so here is the angle that we started with. So to the angle we multiply by pi and divide by 180. So that's what we're going to have to keep in mind. So of course here 90 goes once and twice here, so this is going to be pi over 2 radians. But the thing we're talking about is that if this is theta in degrees and this is theta in radians, then to go from left to right we multiply by pi and divide by 180. So that's from degrees to radians. So that means in part B we have got 210. So this is going to be 210 times pi divided by 180, multiply by pi and divide by 180. So here 3 goes 7 into 21, and 3 goes 6 times into 18. Then the last one is 315. So 315 degrees is going to be, we multiply by pi, we divide by 180. So this time we know that 45 goes into 180. Does 45 go into 315? Yes, it does. It goes 7 times, so it's going to be 7 over 4 radians. Okay, so just make sure that you can do these ones here. So just pause the video for a moment and then have a go, and and then we will show you the answers in a moment. Right, so the 60 degrees is going to be pi over 3 radians. 270 is 3 pi over 2 radians, and 225 is 5 pi over 4 radians. Okay, so in the next question, let's see how to convert from radians to degrees. Alright, so this time we're going to convert from radians to degrees, and the main thing here that we do is simply replace pi by 180 degrees, because remember that pi radians is 180 degrees. So here we've got pi radians here, so simply going to write this as 2/3 of 180 degrees. 3 goes 60 times there, so that's going to be 120. Then for B, we've got pi radians over 4, so that's simply going to be 180 over 4, which is going to be 45 degrees. For C, got 5 pi over 6 radians, so it's going to be 5 on 6 times 180, so that's going to be 150. So please have a go at the other three, D, E, and F, and then you can compare with our answers. Alright, you should have found that 4 pi on 3 radians is 135 degrees, 3 pi on 4 radians 240 degrees, and 11 pi on 6 radians is 330 degrees. Okay, now we're going to look at area and arc length in radians. Area and arc length, but we're going to be interested in this in radians. So if we have a sector of a circle, so sector of radius r, sector of radius r, and suppose the angle here is theta. This is in radians, so the arc length is denoted by the letter S. So the question is, what's going to be this arc length in radians, and what's going to be the area of this whole sector in terms of radians. Right, so for the arc length, from the definition of the radian, this angle here in radians is going to be equal to, so I'm just going to, so that angle in radians is going to be the arc length S divided by R. S divided by R. This is such that if this is equal to R, then this quotient is going to be 1. so we're going to have 1 radian. So from there we can conclude that the arc length is simply going to be given by r times theta. So I'm using capital theta for angles in radians, just like we did there. Okay, so the arc length of this sector here is just going to be given by r times the angle. Now let's compare this with the formula in terms of degrees. In terms of degrees, it's going to be pi d, or 2 pi r times theta in degrees divided by 360. You can see how complicated this thing is. But notice that if we regroup this, we can write it as theta pi over 180, because these two divides with that to give 180. So, and if we take the angle in degrees and multiply it by pi and divide by 100, then this is just the angle in radians. Okay, so that shows us that the angle, or the formula for arc length in radians, is going to be much simpler. Then the same thing, the formula for the sector in terms of degrees is going to be pi r squared, then it's going to be times that fraction theta over 360. So if we move this pi to this side, so I want to multiply this by pi and divide by 180, like we did in that step there. So we're going to have r squared theta multiplied by pi. We have 180 here, but we've got 2 times 180. So we're just going to put the 180 here and bring the 2 this side. Then this now is our angle in radians. So our formula for the sector in radians is just going to be A equals half r squared theta. And the reason why we are doing radians is that indeed in all the mathematics that we're going to see from now onwards, all the formulas simplify tremendously if they're expressed in radians. So that is our formula for the arc length, and that is the formula for the area of a sector of radius r and angle theta, so that theta is in radians. Now let's look at some examples. Right, in this question we've got the minute hand of a clock which is 12 centimeters long, and then the question says in 20 minutes find how far the tip of the hand moves, and then in part B find the area swept by the hand. Let's do a little sketch here. Right, so in 20 minutes the clock or the hand is going to move from here to there. So in part A we want that distance, and then in part B we want that area. So the first thing we need to do is to find this angle here, theta. So, well, this is going to be 1, 2, 3, 4 divided by 12, and then times 360. 2, 3, 4, 5, 6, 7, 8, 9, 11, 12. So 4 over 12 is a third, and then a third of 360 is 120. So that's 120 degrees. If you multiply this by pi and divide by 180, then we can express this in radians. Is 2 pi over 3 radians. Then it means the arc length is simply going to be theta times r. Theta is 2 pi over 3. R is 12. So that's going to be 3 goes into 12 4 times. So this is going to be 8 pi centimeters. It's going to be the distance moved by the minute, the tip of the minute hand. And then in B, we want the area swept. So it's going to be 1/2 r squared theta. So this is 1/2. R is 12. Theta is 2 pi over 3. This is going to give us 24 pi centimeters squared. Alright, let's just give you an exercise to work on. Okay, so in this exercise, you have got a sector of radius 8 centimeters, angle 45. We want the area of the shaded region and also the perimeter of the shaded region. Okay, so please just pause the video, have a go, and then you can continue the video to check and compare with our answer. Alright, so let's work through this. For the perimeter, I've called this side L. Obviously this side is the arc length. We're going to start by converting 45 degrees to radians. So we multiply by pi and divide by 180. So it's going to be pi over 4 radians. So the arc length, which is simply r times theta, is going to be 8 times pi over 4. So the length of the curved side of the region is just going to be 2 pi centimeters. Then the straight side is going to be a bit involving, but we can use the cosine rule. So by the cosine rule, we're going to have that L squared is 8 squared plus 8 squared minus 2 times 8 times 8 times cosine 45. Now so this thing is going to be equal to 8 squared plus 8 squared is 2 times 8 squared, so that's going to be 128 2 times 64. So that's 128 here, minus, this is also going to be 128. Then cosine 45, we will show that it's equal to square root 2 over 2. So this thing is going to be, if we, so this is going to be 128 minus 64 square root 2. It's going to be 64 into 2 minus square root 2. So that's L squared. So therefore L is going to be the square root of this thing. 64 to root 2. So square root 64 is 8. So it's going to be 8 into the square root of 2 minus root 2. Therefore, the perimeter is going to be this number, 8 into this, plus 2 pi, which we found earlier there. And this is all going to be in centimeters. Right. And then the area. So for the area, we're going to have to find the area of the sector first. Then we're going to have to find the area of the triangle. Then we're going to have to subtract this area from this area to find that one. So the sector, again, is going to be, so let's call that one A. S for sector, so just 1/2 r squared theta. So 1/2 r is 8, theta is pi over 4. So this is just going to be 8 pi centimeters squared, because there is 8 in the denominator and 2 of them in the numerator. And then the area of the triangle, going to have to use the trigonometric formula, which says half AB sine theta, where this is theta, this is A, and this is B. In our case, A and B are both equal to 8. So this is going to be 1/2 8 times 8 sine 45. Well, 1/2 of 8 is 4, times 8, so again 45. Sine 45 is the same as cosine 45, root 2 over 2. So this thing is going to be 16 root 2 centimeters squared. And then of course this must be smaller than that, so then the area of the shaded is just the difference between those two. So area of shaded region is going to be equal to 8 pi minus 16 root 2. It's going to be in centimeters squared.